Now it's time for the scariest topic of all, the area under the curve on a graph. This is calculus. Oh man, calculus. But good news, it's the kind of calculus where all you need to be able to do is know that the area under the curve means something. You have to be able to remember what it means on different types of graphs. And you have to be able to calculate the area of some basic shapes like a rectangle, a triangle, or a trapezoid. So let's get started. Now let's say we have a graph of velocity versus time, and our graph shows a horizontal line for velocity right at 5 meters per second. There we go. And just for fun, let's block off an area of this graph. And I'm just going to block off an area, say, from 0 seconds to 10 seconds. And again, just for fun, because we're into such things, let's imagine this shape that's underneath this area, or that's within these boundaries. So defined by kind of the shaded area here. And we'll go from the graph at 5 meters per second down to 0 meters per second. And hey, why not? Let's find that area. So the area for that would be equal to, well, it's a rectangle, so it's length times width. And in this case, the length we'll say is 10, and that's units of seconds. And the width, or the height here, I guess, would be 5 meters per second. And when we multiply those two together, 10 times 5 gives me 50. Seconds times meters divided by seconds, well, the seconds will just cancel out, and I'm left with meters. So what would the meaning for that area be? Well, 50 meters, that sounds like a distance or a displacement measurement. And in fact it is. We find that the area underneath this graph, for an object that's going at 5 meters per second, if we look at the area underneath that for 10 seconds, we get 50 meters. And if we just reason through this, an object goes 5 meters every second, and we let it go for 10 seconds, then it's going to cover a displacement of 50 meters. It's going to end up 50 meters away from where it started. Now, what if we have a more complicated shape than that? Does it still work? Well, it turns out, yes, it absolutely does. The area underneath a velocity versus time graph gives us a displacement during that time interval. So that's the meaning we were talking about before. We need to know that on a velocity versus time graph, if we look at the area underneath the curve, the meaning for that is the displacement during that same time interval for which we blocked off the area. So for us, we blocked off from 0 to 10 seconds, so we're looking at the displacement from 0 seconds to 10 seconds as well. If we have a different type of graph, the meaning will be different. Just like when we looked at the slope of a graph, that had one meaning on a position versus time graph and a different meaning on a velocity versus time graph. The same thing will happen here. So let's try a little more complicated shape, and we'll talk about some additional little rules that go with this. If we have this shape for our velocity versus time graph, when we calculate the area under that graph, we're just going to be dealing with a triangle instead of a rectangle. Or depending on the time range, it could actually be a different shape. We'll look at that in just a minute. But let's go again from 0 to 10 seconds. So from 0 to 10 seconds, I will mark off my areas here. There's my 10 seconds. And 0, I don't need to go. You'll notice that I'm drawing my blue lines from the red line to the x-axis. And at 0, the red line and the x-axis intersect. So I don't really need to include anything here. The area underneath the red curve, then the red line from 0 to 10 seconds, is described by this shading now. Okay, and so my area on this one then, which I know now is equal to my displacement, is going to be equal to, well, the area of a triangle. And the equation for that is 1/2 times base times height. So my displacement for the first 10 seconds here is going to be 1/2 times the base. So that'll be the bottom of the triangle, we'll say. So that's 10 seconds. times the height, and that is 5 meters per second. And so my displacement then is going to be 1/2 times 10, which is 5, times 5 is 25. And units, I've got seconds times meters divided by seconds, so my seconds cancel again, and I've got meters, 25 meters during that time period. Remember, if we were going at a constant velocity of 5 meters per second, we were going to end up with 50 meters covered. But here we're going at 0 meters per second to begin with, 5 meters per second at the end. We could say that our average velocity during that time is 2.5 meters per second. And so in 10 seconds, we're traveling 25 meters. Now what about if we wanted a different time interval, let's say from 4 seconds to 10 seconds now. So I'll draw in my 4 seconds and my 10 seconds boundaries from my red graph to my, my black axis here, and then I'll fill in my shading just to remind myself of what I'm calculating the area of. That shape is one that we call a trapezoid. It's one that has one pair of parallel sides but not a second one, so it's not a parallelogram. You might know the equation for the area of a trapezoid is 1/2 times the quantity b1 plus b2 and quantity times the height. If not, though, that's fine. I tend to just break these shapes up into a triangle and a rectangle. And it works out exactly the same way. So my area now, which is equal to my displacement, is going to be equal to the area of that little triangle, 1/2 base times height for the triangle, plus the area for that rectangle, and that's length times width. So my displacement on this one will be 1/2 times my base on that triangle is 6 seconds, times the height of that triangle. It goes from 2 meters per second to 5 meters per second, so that'd be 3 meters per second. Plus, for my rectangle now, the length is 6 seconds. And the width, or the height here, is 2 meters per second. And so my displacement then is going to be 1/2 times 6, which is 3, times 3 is 9. The units on that, seconds times meters divided by seconds, so just meters, plus 6 times 2 gives me 12. Seconds times meters divided by seconds gives me meters, and so my displacement during that time period is going to be 21 meters. So why isn't that the same as the one we had before? We had 25 a moment ago. Well, that included this extra piece here. So from that we can figure out that the area on this one must be 4 meters, because the area altogether has to be 25 meters, and we know that the sections we just calculated had a total of 21 meters. So it must have traveled 4 meters during the first 4 seconds, and 21 meters during the last 6 seconds, 25 meters altogether during those 10 seconds. Alright, what's all this now? How do we deal with those negative velocities? Well, we're going to have what we'll call a negative area, which is something that doesn't make any sense outside of calculus. What's the area of a room? You'll never have a negative number for that. But we will have negative numbers here. Any area that happens underneath the x-axis is going to be a negative area. So let's look at from 0 seconds to 4 seconds here. We have that beneath the x-axis. So when I draw in my, my blue lines to mark off my time, see that I don't need one at 4 seconds because the graph is right at the x-axis there. So the time I'm looking at is this time, or this area right here. And so the area on this one then would be 1/2 base times height. The area then, and that's equal to the displacement. It's 1/2 times my base, we'll say is 4 seconds, times the height of that triangle, and that'll be a -2 meters per second. Yes, if we had a triangle, that we were just trying to measure, a piece of paper cut into a triangle here, it wouldn't make sense to have one dimension be a negative dimension, but here, since negative and positive velocities have different meanings, we do need to keep track of that information. We always draw our areas, though, from our graph to the x-axis, so I wouldn't ever extend an area over the x-axis. For example, sometimes I see people mistakenly draw something in like this and try and calculate the area of this whole thing. We're going to break that up, though, into parts that are above the x-axis and parts that are below the x-axis. So let's get rid of that. All right, back to this piece. Our displacement then during the first 4 seconds is going to be 1/2 times 4, which is 2 times -2. So it's going to be a -4. Units are seconds times meters divided by seconds. So that's meters. -4 meters during the first 4 seconds. What if we want to know for the whole 10 seconds? Well, we still break it up into parts that are above the axis and parts that are below the axis. And then for the part that's above the axis, I'm looking at this area now. And the area on that one, which is equal to displacement still, is 1/2 base times height, because it's a triangle we're dealing with. And so that displacement will be 1/2 times our base from 4 to 10 seconds is 6 seconds. Our height there is from 0 to 3 meters per second. That's a positive 3 meters per second. Let's go ahead and put that direction information in so we don't forget about it. So delta x then is 1/2 times 6 is 3, times a positive 3 is plus 9. Seconds times meters divided by seconds, meters for our units. All right, and then our displacement overall, our total displacement, you'll see this sign for total pretty frequently here. So our total displacement during that 10-second period is going to be, well, -4 meters in the first 4 seconds and a positive 9 meters in the last 6 seconds. And so that's going to give us an overall displacement of plus 5 meters. We end up 5 meters on the positive side of wherever our object started for this one. If we have a more complicated shape like this one, we might have to get a little bit creative as far as how we break up our areas. For this, we need some regular shape that we know how to calculate the area on. So let's say we want the area for the whole time interval. Let's see, if I put a vertical line right here, I end up with a triangle in this space. If I put another vertical line right here, I get a rectangle here. If I put a vertical line up here, well, that's a trapezoid. Again, if you know the equation for the area on a trapezoid, feel free to use that. Otherwise, we can break up trapezoids into rectangles and triangles. Put a horizontal line there, and then I've got a rectangle here and a triangle here. Add the areas of each of those sections together to get the total area during that time interval. Jiminy Cricket, aren't we done with this yet? Not quite. We also have to talk about curves. What happens if we have a curved graph? Now, we tend to work with constant acceleration situations, and so these are less common for us at AP Physics 1, but absolutely in the real world we'll see curved graphs when we're doing data collection. So how do we handle that? Well, one, you could know calculus. We don't assume that you do here, so you don't need to know any calculus to do this one. You do have to know how to count boxes, though. We're going to make an approximate answer here, or make an estimate on this. So let's say we want to know the displacement from 0 to 5 seconds. So I'm going to go ahead and get my area rounded out here. So we've got our boundaries on this one. All we're going to do is count the number of boxes within that area. And then figure out how much each box is worth, and then we can make a pretty good estimate on how many meters are traveled here. So for counting boxes, since we have these partial ones here, a way that is accurate enough while still being quick to do this is I'll count all the whole boxes first, and then I'll count all the partial boxes, and I'm just going to treat each partial box as though it were half a box. So some of them will be a little less than half, some will be a little more than half. On average, it works out okay. There is some interpretation on these, so we should fall within the wiggle room of grading for these ones. So whole boxes first. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. 32 boxes. Okay, and to that I'm going to add, remember I'm only counting every other one here, I'm treating them all as half boxes. Tap 1, tap 2, tap 3, 4, 5. Okay, that gives me 37 boxes altogether for an area, but how much is a box worth? Well, looking at my scale, I see that each box, I'm going to zoom in a little bit so we can see this a little better. Each box has an area, each square here has an area, or has dimensions of half a second wide by 5 meters per second tall. So if I would find the area of a single box, then I would do 5 times 0.5, so that's 2.5 meters divided by seconds times seconds, so 2.5 meters for each box. So 37 boxes times 2.5 meters gets us to our approximate answer anyway, and that's going to be 92.5 meters. That's our displacement from 0 to 5 seconds approximately. One last thing we need to know about here, and wait a minute, didn't we already do the horizontal line one? This is the acceleration versus time graph, not a velocity versus time graph. Well, what does it mean if we take the area underneath an acceleration versus time graph? Let's say for the first 5 seconds here, so from 0 to 5 seconds, let's figure out the area, and then once we have a number, we can decide what it means, or figure out what it means. So we're looking at this area here. Our area is going to be length times width, because it's a rectangle. Our length is 5 seconds. Our width, or our height here, I guess, 3 meters per second squared. And so our area then is going to be 5 times 3 is 15. Units, we've got seconds times meters divided by seconds squared. So I have one factor of seconds that cancels and one factor of seconds that remains. My units on this would be 15 meters per second. Hey, that's a velocity. So is that the velocity that it's going at 5 seconds or at 0 seconds or... Well, actually, we don't know what velocity it's going at 5 seconds or at 0 seconds. What we do know, though, is that our velocity at 5 seconds is positive 15 meters per second more than it was at 0 seconds. This area is going to represent not the velocity, but the change in velocity. Just like on a velocity graph, the area represented the change in position, not the position itself, but how much the position changed during that time. Well, here, during the time from 0 to 5 seconds, our velocity changes by plus 15 meters per second. And again, we can reason our way through that. We have an acceleration of 3 meters per second. So every second that goes by, we change by 3 meters per second. We let it go for 5 seconds, so yeah, it's going to change by 15 meters per second. So to summarize, regardless of the shape that we have on one of these graphs, on a velocity versus time graph, if we find the area under the curve for some time period, what we're solving for is the displacement during that time period. If we have an acceleration versus time graph, we find the area under the graph for some time period. We're finding the change in velocity for that same time period. What about if we had a position versus time graph? Well, in that case, we have a meaningless area. You can calculate it, but it doesn't help you do anything. That's it for areas under graphs. Get plenty of practice with trying out both types of graphs here, doing the velocity and then doing some acceleration graphs. The tricky part on here is keeping straight what the areas mean, and we're going to throw back into this what the slopes mean on each of these graphs. The calculations themselves aren't too bad, but keeping everything straight in our heads, that can be a challenge. Thanks for watching, folks. We'll see you next time.